Welcome to India's most comprehensive e-learning platform, BYJU'S Exam Prep. Myself, Phanindar, I am here to present the subject called Process Control Instrumentation. In this evening, we all are gathered to discuss the concept of proportional controller. Along with that, I will also explain the concept of on-off controller. But before getting into the actual topic, let me quickly explain about myself. As you can see on the slide, all put together, I have an experience of 11 plus years of teaching, and I have guided more than 50,000 students, putting ECE students, electrical students and instrumentation students together. In fact, I have delivered a lot of content in the subjects of control system, circuit theory and industrial instrumentation all put together. And I am specially known for industrial instrumentation topic. As we all gathered here to discuss the concept of proportional controller as well as on-off controller, I don't make any delay. Let's get into the topic straight away. Well, before going into the topic, I would like to recap what happened in the previous session. Anybody remembered about the previous lecture? I'm very sure that most of the students are new to this lecture, but trust me, if you've gone through the previous lecture, then this lecture is a cakewalk to you. However, even if you have not attended the previous lecture, don't worry about that. I will take you from the basic lecture till the end. The only request from my side is be with me till the end of the lecture. I'm very sure you all will enjoy a lot. Well, I'm seeing some students here. Vijay Srinivasan, good evening sir. As very good evening Vijay, and very good evening to all of you. So let me take 2 to 3 minutes to explain the previous day concepts. Well, so you can all see there is a title here that is called liquid tank. In fact, we have named that as a liquid level tank, isn't it? There are two pipes connected to the tank. One is above the pipe, above the tank, and there was one more pipe which is just connected at the bottom of the tank. So there are two walls. One is called V1 and the second one is V2. Okay, very good. I am just explaining the previous day concepts so that you all can cope up with the regular flow. So we have seen that this is a liquid level tank. Of course, when the fluid is flowing through this particular pipe, we named this flow rate, which is actually flowing into the tank, as input flow rate, and we named that flow rate as Q naught of T. Correct? I hope you all remember the previous day lecture, right? So you can all see there is a pipe which is connected even at the bottom of the tank, and the fluid which is coming out of the tank, that is rated as Q naught of T, and we called this as a output flow rate. Correct? So there are two important parameters which we have discussed in the previous lecture, that is input flow rate, and followed to that we have also seen output flow rate. What was our objective here? We have seen, suppose if the input flow rate is somewhere around 10 liters per second and output flow rate is somewhere around 5 liters per second, we understood that the water gets accumulated inside the tank, and the detailed discussion was done in the previous lecture. That's why again and again I am saying that if you have already watched the previous lecture, this is going to be cakewalk to you. And I sincerely request every one of you, please follow the continuous flow till the end of all the lectures, then only you will enjoy the topic. Well, what was our main objective in the previous lecture? Any one of you? Hello, good evening everyone. Sir, please share this PPT, it's very useful to us. Yes, Sangeeta definitely will share that. So our backend team will definitely message you and they will help you in this. Don't worry about that. So what was our main motive in the yesterday's session? The water level in the tank has to be maintained exactly at 1 meter, correct? So putting the statement straightforward, this was the control problem what we have discussed in the previous lecture. Whatever may be the tank, I don't worry. Whatever may be the flow rate, I don't worry. Whatever may be the situation, I don't worry. But ultimately, the water level should be maintained at 1 meter. And the water level with respect to time, it was mentioned as H of T clearly, right? So these were the basics what we have discussed in the previous lecture. Moving ahead, how we can maintain this water level exactly at 1 meter? To maintain this water level at 1 meter, irrespective of any situation, we have created an additional system all put together that is called as a automatic system, correct? Or the process is called as automation. Have you remembered all these things? I want the reply from all of you. To maintain the height of tank. Very good, excellent. Right. So I'm very happy to see the replies from you and grateful to be here. Yes, very good. So our idea is to develop a system which can maintain the water level exactly at 1 meter, isn't it? For that, we have taken the help of first device that is called level transmitter or level sensor, correct? So in short, we call that as a LT. And then this level transmitter will inform the data to the error detector, or we can even see this as a subtractor here. What it is doing? It simply subtracts the data of the water level with the water level what is required, and then pass the information to the next device that is actually nothing but level controller, correct? So that is another important device which is to be there in the additional system, and the level controller all the way see the error, and based on the value of the error it will regulate the valve position. That means ultimately the level controller will either open this as per the requirement, or it may close the valve as per the requirement. So when it is changing the position of the valve, quite logically the flow rate here will going to change, and ultimately the water level will be maintained at desired value, that is nothing but 1 meter. So this was a discussion I have made in the previous lecture very clearly, and of course all of you really enjoyed this lecture, right? Now in this lecture what we are about to discuss. So let me put the block diagram of this all put together. We know the set point here is equal to how much? Any one of you, what is the set point here? Shivani Sharma. What is the set point? We have discussed in the previous lecture. Deepak Rawat, Rishabh Yadav, good. So the set point what we have discussed in the previous lecture is 1 meter. Irrespective of the situation, we need to maintain the water level at 1 meter. And we have clearly seen that the water level is continuously monitored by a sensor or transmitter, or in fact you can call this as a transducer also, I don't mind, right? The error will be detected exactly here after the subtractor, and the error will be given as an input to the controller. And this is a point you must remember till the end of the last lecture, then only you will be able to understand the whole session. The input to the controller is what? Again and again I am asking, what is the input to the controller? Well, very good. Error, error, error. Nice. Nice to see many of you are following exactly the class. So the error is being the input to the controller, and we have seen clearly, of course, in simple language, we do represent this particular error as E of t. Clear? Means error is actually time dependent, right? And more importantly, after the controller, we have seen the current will come as an output here, correct? So the current whichever is generated here, current or voltage, basically it is a electrical output. So the controller will generate the electrical output, and that electrical output of the controller will be given as an input to the valve. Clear? Suppose if you use electrical actuator or solenoid valve here, solenoid valve can understand the current so easily, so no problem. So it will regulate according to the current generated by the controller. But in case if you are having a pneumatic valve, okay, so look at the beauty of this one. Suppose if you have a pneumatic valve, what should be happen? If you have a pneumatic valve, it cannot understand the value of the current. So we have to change this current to the pressure first. P stands for the pressure, and once the current is changed to the pressure by I to P converter here, so let me write down I to P. I/P means it is I to P converter. Once the current is changed to pressure, then the pressure will be operated on the pneumatic valve, and finally it will change the flow rate of the process or the liquid tank. Clear? So this is exactly what we have concluded in the previous lecture. Now I would like to mention a point here. Every one of you please see this. I to P converter, very good, excellent. So the I to P converter plus valve, pneumatic valve, together it is called as actuator. So please see and try to understand, this is a very important statement. I to P converter plus valve, together it will be called as actuating system, or if both of these two are combined, then we call that as a actuator. Clear? When do we really require actuator? If the controller is generating current and the valve is not able to understand the current, if the valve is pneumatic valve, then we require a device to convert the current into the pressure, and then that pressure will be operated by the valve. Clear? So I to P converter and the valve, together it is called as a actuator. Suppose if the valve is able to understand the current, if the valve is able to understand the electrical output generated by the controller, in that case, we don't really require the I to P converter. A simple valve is sufficient. Clear? So I have explained the block diagram of liquid tank clearly, and we have named this very clearly that I to P converter and pneumatic valve put together, it is called as a actuator. So how does the real time or the general block diagram of control system looks like? So interesting, isn't it? So this is the general block diagram. The previous block diagram is only specific to the liquid tank. But now if you see this block diagram, then you will understand the whole control system can be accumulated in this particular block diagram. Okay. So as you see earlier, the set point, usually we write the set point as R of t. Now you must understand this fact. Again and again in the course of discussion, I regularly put this point. Sometimes I say R of t, sometimes I say 1 meter. But you must understand both are related to each other here. Clear? So R of t is considered as a set point. Sir, if solenoid valve, then that is also actuator. Yes, yes. So because ultimately the valve is converting the electrical signal to mechanical output. If any device converts the electrical input to the mechanical output, then that particular device is called as a actuator. Clear? Very simple. No need to make any hangama. If a device converts the electrical input back to the mechanical output, then we call that device as actuator. Clear? Now moving ahead, here in the general block diagram, we have the set point that is called as R of t. Now look at the previous block diagram. The output of the control system in real-time application is water level with respect to time. But in general block diagram, we will say that is equal to C of t. Clear? And in the previous example, we have level sensor or level transmitter, but now I am generalizing that like a feedback setup. Means I can go with the transmitter, or I can go with the sensor, or I can go with the transducer depending upon the situation. But in real-time process industries, we will use the transmitter. Clear? So that is about feedback. And we have controller very clearly here, and actuator is also there. Now you have to understand, even if you have only solenoid valve, that would be called as an actuator. If you have a pneumatic valve, I to P converter plus valve, together it will be called as an actuating system or actuator. And then actuator will operate on the process here. Clear? So now let us go to the variables here. Have you seen the most important variable here is error, which is considered as with respect to time. So that same thing I have mentioned here. So the error with respect to time here, very happy. And the current what we have taken in the previous example, which is considered or which was considered as the output of the controller, right now I am changing the alphabet and considering this as a P of t. Why? Because some controllers may generate the current as output, some controllers may generate the voltage as output, right? So that's why, to generalize the concept, let me use the alphabet like P of t. P of t is considered as the output of the controller. Now, when the output of the controller is given as the input to the actuator will receive this signal and generates the manipulated signal with respect to time. In the previous case, that was the input flow rate. Clear? Am I clear so far, all of you? Mention in the chat box. I will be really very happy to see all of your messages, and I can answer if possible. So please, every one of you participate in the class and reply to me. Is it clear to everyone so far? I have came up to the general block diagram. I have compared the general block diagram with the real-time liquid level tank. Clear? So hereafter, whenever I say set point, you can mention simply like R of t, or you can simply mention like 1 meter. Okay? If I ask what is the output, you can simply say like C of t, or you can simply put it like a H of t. So that our general block diagram and practical application both will go hand in hand, and your concept will be so clear. In fact, damn clear, and nobody can beat you. Okay? Right? Clear, clear. Very good. Thank you very much. Right. Now, what is our session? You may ask a question to me. Fine, sir, all these things we know. In fact, we have studied in every book all these things. But to understand the next half an hour section, you must understand all these things clearly. That is the reason why I have clearly mentioned everything. Now let's go one step beyond this. Okay? So what is our objective of the discussion? Our objective of the discussion is to discuss the controller, right? So now let us take only a small block here. So let us assume that all these things are, not so important as of now, okay? So let me worry about only the controller. When you look at only this controller, in the overall closed loop control system, what is the input to the controller here? The input to the controller is error signal, and I have specifically mentioned that when the error is given as the input to the controller, the output of the controller is taken as P of t, correct? So let me take only that controller part and say the input signal to the controller as error and the output of the controller as some current or some kind of output. Let me take that as a P of t. It may be current, it may be voltage, sometimes even pneumatic controllers also there. So that will generate the output as a pressure. So whatever it may be, controller output is considered as P of t. Is it clear to all of you? Everyone, Santosh, clear? Sai, Varun, clear? Very good, excellent, excellent. So all of you please be active in the chat box. How much you are energetic, the same energy I will be having, and I will do my best, okay? Right. So what are the expectations of the controller? Being an instrumentation engineer or being a control engineer, what are your expectations from the controller? So in the previous lecture I told you, irrespective of anything, the water level should be maintained at 1 meter. So if I write in a simple word, it should make sure the entire closed loop system to be stable, correct? Because when the controller is there, even if the system is going to become unstable, it should take care about everything and make the closed loop system stable, right? So if the closed loop system is stable, then only we can do something about it, right? If the system is not stable, we cannot do anything about that. So the duty of the controller is primarily to monitor the whole stability of the whole system. If it is not stable, it has to stabilize the closed loop control system. I am repeating, closed loop control system. This was the first target of the controller. And moving ahead to the next one, it should operate to make steady state error equal to 0. This is the very second important point, but you must understand what you mean by error. We have seen that error E of t is generally considered as R of t minus C of t. This is what I have explained even in the previous class, right? So if you see the practical application, what would be the error here? The error would be written as equal to the set point. So H set of t minus H of t, correct? So if I say the error became 0, what does it mean? The error became 0 means what? Any one of you, fatafat tell me the answer. Sir, aap kyun practical? Okay. So because we have to understand the session very clearly, right? So that is the reason why I'm making it all these things. Now I'm asking why the error should be 0. So if the error becomes 0, what will happen? If the error is equal to 0, it inherently means that 0 is equal to R of t minus C of t here, correct? So this means I can say after some time at least, the value of R and the value of C both will be equal. It means that the water level will going to become like H set, that would be called as a 1 meter here. Clear? So this means making the error is equal to 0 really means that getting the required value, nothing else. Clear? So that is the primary responsibility of the controller. Clear? Yes, input is equal to output. Excellent. R of t is equal to C of t. Nice. Very good. System is stable. Right? Now the third one is it should operate to generate the desired response as fast as possible. Clear? The third point is all about the speed of response, because we can't wait near to the tank and see the tank for 1 hour like this to get the water level 1 meter. Correct? We want the water level to be reached to 1 meter as early as possible. Maybe in 5 to 10 seconds, correct? So that's the reason why third important point is speed of response. So what are the 3 important expectations from the controller? You use any controller. You use proportional controller, you use on-off controller, you use integral controller, derivative controller, anything you use. 3 important expectations as a control engineer out of the controller are: first one is it should make the closed loop system stable. Second is the steady state error should be 0 for accuracy purpose. And the third one is speed of response. Clear? So is it clear to all of you? Sir, Like we have industrial current range, don't we have industrial voltage range? Yes, we do have industrial voltage range. In fact, the current range 4 milliampere to 20 milliampere will be converted to voltage at the receiver side. Transmitter will send 4 milliampere to 20 milliampere from the field level, but at the receiver level or at the receiver channel, the 4 milliampere to 20 milliampere will be converted to voltage. Clear? But we don't transmit the voltage. Remember this point. Okay? So this is all about the expectations of controller. Now here it comes the most important topic of the session, that is proportional controller. Well, I have taken almost around 20 minutes of time to come to the actual topic, but hope this 20 minutes of section really useful to you to understand this topic very better. Clear? So we have error as an input to the controller, and let me not go with the current, let me take this as a controller output for some time being. Clear? And as I was saying, controller output right now I am writing as P of t. Correct? What is actuator means? Actuator means it's a device which converts the electrical input into mechanical output in a simple language. Clear? So here if you see, error is the input, output is P of t. Now I will ask a simple question. Look at that. From now onwards, the real depth of the process control will start, and I am very sure those who are with me, all these 40 students, they will understand the subject very, very clearly, right? So what if the controller output is proportional to the error signal? Simple, very simple, isn't it? Controller output is P of t, I am saying this point, is directly proportional to error signal, correct? If this happens, then this particular controller is called as a proportional controller. Simple language, nothing else. Okay? Proportional controller. That means if the output of the controller is directly proportional to the error signal, that controller is called as a proportional controller. But as you all know, in engineering, we don't appreciate the proportional symbol. Rather, we will remove that proportional symbol and keep some kind of constant there. Clear? So therefore, we can say here P of t would be equal to some kind of Kp here, okay? We will use some constant here into E of t here. Clear? So now you must understand this fact clearly, that this Kp is called as controller gain. Clear? Because in fact if you see, both error and P of t, both must be in the same language. If the units are same, then the ratio of output of controller to the input of the controller, what it will be called? In fact, it will be called as a gain only, right? So because if both of them are having the same units, then it will be called as a gain, and that has to be represented as Kp because it is proportional controller. Clear? So I hope you understood the logic behind the proportional controller here. So all of you please say yes if you are understanding the logic or not. Or do you want me to explain one more time? Every one of you. If used 0 milliampere हम process का पता है? Yes, correct. Of course this is correct. Deepak, very well done. Right. So I'm asking that P of t is equal to Kp into E of t. But what would be the transfer function of this? Because if you apply simply Laplace transform on both sides, look at that. See, you must have to go through the basics of control system to understand the process control clearly. Otherwise, I can't do anything. You require little bit basics of control system to understand process control very, very clearly. Okay? Apply Laplace transform on both sides. If you apply Laplace transform on both sides, easily we can say that P of S, right? Capital P of S, that is equal to Kp into the error signal E of S here. Clear? Now moving ahead, I can take a very simple ratio here, P of S divided by E of S, and we can call this as Kp. And P of S by E of S, what it is called as? Any one of you? Anyone? P of S divided by E of S, we call that as a Laplace ratio of Laplace transform of output of the controller to the input of the controller. This is called specifically as the transfer function of the controller. We represent the transfer function of the controller as Gc of S. Clear? So this is very, very important to understand. Gc of S is the transfer function of only controller. And from this, we will go one step beyond that and try to explore the closed loop control system. So far, I have explained only the transfer function of transfer function of proportional controller. Clear? Now let's try to investigate what happens if I put this controller in the closed loop control system. Hereafter the concept will become so difficult. So I request you to please be attentive in the class, answer to me. Okay? Every one of you please continuously watch the session, then only you will understand the session. Now this controller, whatever we have here, let me take other color. I am sure you will mess up with the things here. So we have a controller here. Oh my god, let me take another color, no issue. Well, so the controller here, it may have the transfer function which is called as a GC of S. Interestingly, actuator is there, and for actuator is also there is some input here and some output. So it will also have some kind of transfer function. Let me take that as a GA of S here. Clear? So we have a feedback setup here, and people do represent the feedback as H of S because they are very lazy. Instead of writing something else, they will going to make this as H of S because this is a standard notation. So let us use the H of S, right? So this H of S is considered as a transfer function of the feedback. Clear? And more importantly, the process transfer function, let me call this as GP of S. Okay, GP of S is considered as a process transfer function. Clear? Now let me put some of the important, very important conclusions here, and that will lead to the structure of the whole closed loop control system. Okay, so what I am doing here is, first let me take a unity feedback system. Don't argue with me like, sir, why you took unity feedback system? I don't want to take unity feedback system. No issues, you can take whatever you want, but first let me make the things simple. After that we will include the complexity. Don't worry about that. Let us make H of S is equal to 1. At the same time, for simple understanding purpose, let me take GA of S also as equal to 1. Okay. So if that is the case, what are left here? Now we have left with only GC of S. What is GC of S in proportional controller? Any one of you? If GC of S is required here, so GC of S is considered as a proportional controller here. So let me say that proportional controller value as KP here. Clear? And GP of S, intentionally we have taken the process here. And for example, if you take liquid level tank, in a simple note, the transfer function of the process can be considered as a simple first order system which has a transfer function of K by 1 plus tau S. Clear? So you must understand, sir. Yes, very good. Okay, so we'll go ahead with that statement. Don't worry about that. GP of S is nothing but plant transfer function, and this plant is now nothing but the liquid level tank, and this is a first order system. Correct? Right now, GC of S is known to you, GP of S is known to you, and GA of S also known to you, and even H of S is also known to you. Now putting all this together in a closed loop system, this is how exactly it looks like. Isn't it interesting? Right? Now we don't have H of S. Why? Because the H of S is equal to 1 here, so I don't worry about that. And GA of S is also not visible here because that is also 1 here. Only controller and the plant transfer function both are visible here. Controller and process together. Correct? Now I would like to ask a question to every one of you. Controller is operating over the process with the help of actuator, but what would be the closed loop transfer function here? So can I call this all put together here? So please see, try to understand. We don't require to use any formulas here or any great mathematics here. Very simple basics are required. The only thing is you must have the patience till the end and stay connected to me. Okay, right. So this total diagram put together, in fact it will be called as a G of S, and people do write this G of S right now as GC of S into GP of S. This is very important, right? Now when I multiply this controller transfer function with the process transfer function, putting together, it will come down to be equal to KP, that is proportional gain, into K. Let me write down slowly here. Okay, so KP into K here, divided by, we have like 1 plus tau into S. This is just only G of S. However, we have seen that H of S is equal to 1. So for this closed loop control system, how do we really evaluate the transfer function of the closed loop control system. So let me take closed loop control system, or let me write down one word here so that you will be better understanding here. Okay, the transfer function of, look at this, transfer function of closed loop control system. What it is here? The transfer function of the closed loop control system can be written as C of S divided by R of S. Simple, very simple, right? So this could be written as equal to G of S divided by 1 plus G of S into H of S. Now do you have all the values here? Of course we have each and every value here, right? So what would be this one here? So G of S is how much here? G of S is given like Kp into K divided by 1 plus tau S, right? So therefore let me put all these things here, Kp into K divided by 1 plus tau S whole divided by, we can say 1 plus Kp into K, of course, divided by 1 plus tau S and into 1. Mathematics is a little bit boring, isn't it? But of course, control system and mathematics both goes hand in hand. We can't do anything apart from this, okay? Right? So moving ahead with this, the closed loop system transfer function C of S by R of S could be written as equal to, if you take LCM and cancel this, then it looks like Kp into K whole divided by 1 plus tau S plus Kp into K. This is how we introduce the control system or controller in the closed loop control system. Clear? So we have introduced the controller. Tomorrow we will see integral controller. Even in that case also, we will take the integral controller and put it in the closed loop control system to find out the closed loop control transfer function. Day after tomorrow we will see derivative controller. Again we will take the derivative controller and put it in the closed loop control system to see what happens with respect to the closed loop control system. Clear? I hope you are following this, right? So if you are following this, say just clear to you, all of you. Is it clear to everyone? So far we have fought very much and found just only the closed loop transfer function of overall control system when proportional controller is present inside the closed loop control system. Clear? Now moving ahead, let me take the transfer function of the closed loop control system here. CLCS means it is considered as a closed loop control system. That is equal to C of S by R of S, that is equal to Kp into K divided by 1 plus Kpk plus tau S. Correct? Just before the slide, I have proved all these things. Correct? Now moving ahead with this, can I write this one like this in a simple language? C of S divided by R of S. Specifically, if I take, look at that, 1 plus Kpk in the denominator, I will take outside. Let's see what will happen here, right? So if I take that outside, so in the numerator it looks like 1 plus Kp into K here, right? In the denominator, so specifically it will become like 1 plus tau divided by 1 plus Kp into K all together into S. Correct? So I can say very clearly that this total function, let me write down this as a K dash here. Clear? Of course, I too agree with this. This is a little bit having, a lot of mathematics, but don't worry, because those students who are already exposed to this mathematics, so it looks very easy for them. But this is K dash divided by 1 plus this total tau divided by 1 plus Kp into K, all put together it is called as a tau dash into S. Clear? This means the time constant right now we can see clearly, the time constant tau dash, right? So is equal to tau divided by 1 plus Kp into K. This is a catch, and this is a very, very important statement in this particular line. Now if you see all put together, this tau dash is equal to tau divided by 1 plus Kp into K. Any one of you, what you have understood out of this? Please let me know. So look at this. This tau is actually nothing but the time constant of the process. Correct? So let me write down, this is the time constant of process we can say, or even plant also, right? Time constant of plant. Open loop plant. Because in open loop only we have K by 1 plus tau S. But this tau dash is the time constant in the closed loop, right? So let me write down clearly here, that is time constant of closed loop control system, that is CLCS. Now you should tell me which is high, which is low, right? So everyone who has a minimum common sense, they can understand that if I increase the KP value, look at that. If I increase the value of KP, as KP is there in the denominator, obviously the total value in the denominator will going to increase, right? If it is increasing, this tau dash value will going to decrease, correct? So the tau dash is actually less compared to the value of tau, correct? So what is the meaning of this? Anyone? I want to see your response in the chat box. So please tell me, what do you mean by tau dash is less than tau? Very good. Speed of response increases, the time constant decreases. Excellent, Shivani. I'm very happy to see you here and your responses also. So it means that when we introduce the proportional controller in the closed loop control system, the overall closed loop control system is faster compared to the open loop transfer function of the plant. So is it good or bad? We have seen 3 different expectations of the controller. Have you remembered that? Out of these 3, now this is okay, correct? This is satisfied because it should operate or generate the desired response at the faster phase. And now we are able to see that the time constant of the closed loop system, that is tau dash, is actually less compared to the value of the time constant of the simple open loop plant. And this way, the closed loop system is faster in generating the response compared to the open loop plant. So the third specification is the one we got it, right? Very happy about that. Now moving ahead to the next level, that is steady state error. This is very, very important point. I have seen many times these questions are regularly asked in not only in the GATE examination, even in the PSU interviews also, and even if you go to any job, when you are working in PSUs, you have to do all this stuff, okay? So let us see what is the meaning of steady state error first of all. So for understanding the steady state error, first of all, let me tell you the concept of error first, right? And here, whatever I am giving, that is the authenticated information. Don't get any, misconclusions here, improper conclusions. Let us take the value of the error, general error. General error, what is the value? So we have seen that as E of t here, and we have understood that that error E of t is equal to R of t, that is the desired set point, minus the control system output, that is nothing but C of t. Clear? R of t minus C of t. Now, I would like to ask a question. What do you mean by steady state? The steady state means at t is equal to infinity, right? At t is equal to infinity, this would be written as E of infinity in a simple language, that is equal to R of infinity, of course, minus it would be called as a C of infinity, correct? So this is called as a steady state error in language, right? So the steady state error is nothing but error at a time t is equal to infinity, clear? But we all know that we cannot go for the time domain approach. We have to use something which is very relevant to us in the frequency domain. So people do say that E of infinity is equal to limit s tends to 0 s into E of s. This is called as a final value theorem in the Laplace transform. I hope you all people might be knowing about this. So E of infinity is considered as a limit s tends to 0 into s into E of s, right? Similarly, R of infinity and even C of infinity also, right? So therefore, let me put a simple word here for that even the young students who are studying the graduation, they can also understand very easily, right? So R of infinity means this can be written as limit s tends to 0 s into R of s here, and this C of infinity can be written as limit s tends to 0 s into C of s here. Clear? So therefore, all put together, the steady state error in a simple language, it is equal to E of infinity, which is actually nothing but limit s tends to 0 s into E of s we can take, correct? That is equal to limit s tends to 0 s into E of s can be written as R of s minus C of s. Wow, excellent, right? So people are having, in fact, so many students, they study so much of nonsense here, and they will look at so many formulas like for type 0, type 1, type 2, so many formulas. You don't really require all this stuff. simple logic is steady state error means the error at t is equal to infinity, and whatever I have discussed, that is more than sufficient. So from now onwards, whenever I say steady state error, the only thing that should come to your mind is, look at this, steady state error, which is equal to limit st, in fact this is nothing but e of infinity, that is equal to limit s tends to 0, s into, inside the bracket we will be having like r of s minus c of s. Is it clear to everyone? So I think I am taking a lot of time to explain, but I need to explain all these things so that the even BTech students also can understand this. Okay, so steady state error is equal to this, which is equal to limit s tends to 0, s into r of s minus c of s. But what is c of s here? Can I do a small mathematics here? Because right now in the expression we have c of s. Let us take out this r of s here and keep r of s here. Correct? That is how we will going to get the value of c of s. C of s is equal to this total function, of course, that would be multiplied by r of s here. Correct? Now, if I take this c of s and substitute here, look at the magic here. Okay? So the steady state error, as I said, e of infinity, that is equal to limit s tends to 0, s into, here inside the bracket we have r of s, of course, minus, what is the value of c of s now? C of s is r of s into, we do have value, let me erase this one because it looks so odd here and I don't have the space also, so please have some patience to listen till the end. Okay, so r of s into, what should I say, kp, of course k divided by 1 plus kpk plus tau s, isn't it? Excellent, right? So I'm very happy to see people are so consistent here and listening with the patience. Okay, very good. Right, so the steady state error, as I said, I can take out this one, limit s tends to 0, s into, we can take r of s outside, and inside the bracket if you take a small LCM, okay, so it looks like 1 plus kp into k plus tau s here minus kp into k. Those who are having the pen and paper, you can start working on the pen and paper, start working with the pen and paper so that you will really enjoy the beauty of the subject here. So 1 plus kp into k plus tau into s in the denominator here. Now I can say clearly kpk and kpk both will be getting out, and if I take r of t as a unit step input, let me take r of t, which is called unit step input. So unit step input means it will be 1 into u of t, of course, right? So therefore, what is the r of s value here? R of s is actually nothing but 1 by s, correct? Now, once you understand that this is the Laplace transform of the unit step input, bring that and substitute here, you will really enjoy a lot, okay? So, limit s tends to 0 here, s into r of s is 1 by s now, of course, and when I substitute s is equal to 0, in fact, s will get cancelled here, and we have here 1 plus tau s divided by 1 plus kp into k, of course, plus tau s. Now, substitute s is equal to 0. Clear? So when you substitute s is equal to 0 here, I am very sure the steady state error will become like 1 divided by 1 plus kp into k. Is it clear to all of you? Very good, Deepak, very good. So what we have got, after this much of elaborated explanation, at the end of the whole discussion, we understood that the steady state error, in fact the people do call that as e of infinity, that is equals to 1 divided by 1 plus kp into k. Clear? Right? So k is actually nothing but the plant gain. Kp is the controller gain. Kp is the controller gain and k is the plant gain. Now is it clear to everyone? So please answer yes or no. Okay? So that then I will understand. Now what were the expectations of closed loop, controller in the closed loop control system? So we were done with the third one, the speed of response is increased. But the first one, we have to check that. But if you see the second one, it should operate to make the steady state error is equal to 0. That is our very, very important expectation, isn't it? So therefore, if you go back and see the steady state error calculation now, you will understand that steady state error is a function of the controller gain kp. Clear? So what does it mean? If the value of kp is increased, if kp is very, very high, then only the steady state error will going to reduce. Clear? But what is the ideal situation? Ideally, Look at that. Look at the beauty of this one. Ideally, we expect the steady state error to be equal to 0. This is possible to happen only if it will become 0 if and only if Kp is equal to infinity. Clear? But in real time or else in a practical situation, we cannot get this case. We cannot make Kp is equal to infinity. But we can increase the value of Kp up to certain extent, but we cannot make this is equal to infinity. If we cannot make this is equal to infinity, you cannot make the steady state error is equal to 0. What does it mean? If you cannot make steady state error is equal to 0, I cannot say this is accurate. What does it mean? It cannot be accurate in the sense we will never reach the desired target by using the proportional controller. This is the meaning of this statement. Clear? So, when we increase the value of Kp, I can say the steady state error is decreasing. And in the previous slide, we have seen that if we increase the value of Kp here, the time constant value tau dash is actually decreasing here. So that was one of the great news here. So there are two things which are happening here. When we increase the value of Kp, the time constant value is decreasing. Along with that, crazily, when we increase the value of Kp, even the steady state error value is actually decreasing. So, increasing the value of Kp can bring you two advantages here. First one is the overall time constant is reducing tau dash, and importantly the steady state error is also going to reduce here. Clear? But how much value we can keep? Kp is increasing means we cannot keep the Kp value equal to infinity, right? So, the ultimate objective of the controller engineer or instrumentation engineer is to find out what is the best value of Kp that can really bring your requirements. Because as personally I know, I cannot keep the Kp value equal to infinity, and you also know that you cannot keep the Kp value is equal to infinity. Then what is the best value of Kp? That's the meaning, right? So, now putting it all together, the response of closed loop control system specifically to unit step input with the proportional controller. What does it mean? And this is very, very important. Now I would like to mention this point. Even if you go to any PSU interviews like BARC, RS, even if you see the gate papers, you will understand this kind of diagrams so much. We have a step input here, unit step input, and this red color clearly says that the desired target or the desired value, right? Desired target. Or we can even call this as a set point also. Clear? But now, if you see the response is actually varying like this, and unfortunately, after a lot of time, if you see, there is a gap here, right? So this gap is people used to call this as a steady state error, and we call that as equal to E of infinity. Clear? So, suppose if I increase the gain, what will happen? As I said earlier, if we increase the gain, the speed of response will increase and the steady state error will reduce. So this means, suppose, let us call that here we have a gain Kp1, right? At that time we have a like steady state error like this. Suppose if you increase the Kp value or the controller gain if you increase, then the response will all the way take up like this, right? So this response may be Kp2 here, means when we use the controller gain Kp2, of course Kp2 is more than Kp1 here, right? Clear? So that means in the second case the controller gain is more than the first controller gain. In that case you can really see surprisingly the error here, steady state error here, it is going to reduce. You may ask a question to me, sir, how do you know that? So in the previous slides I have explained, isn't it? When we increase the value of controller gain, steady state error will reduce and the speed of response will going to increase. Then I can say this is the first case and this is the second case. So which is faster and which is accurate? Anyone? First case or second case? Sai Varun, process will not reach set point. Yes, excellent, correct. Of course, process will not reach the set point. That is the major setback or the drawback of the proportional controller. Good. So out of 1 and 2 cases, second case is better than the first case. Obviously, because the speed of response is more and the accuracy is good because the steady state error is less. This is the reason why people are going to increase the value of Kp so much. But if you keep on increase the value of Kp, there is one important factor called proportional band that will reduce. So we have to discuss about the proportional band in the upcoming slides. So that's why be with me till the end of the session. I am sure you will enjoy a lot. Okay. Going ahead in the real-time application. So in the real-time application, In this level controller, if I use the proportional controller by using any of operational amplifier setup, okay, proportional amp controller if I use here, what happens here? Any guess? Look at the beauty of this. The set point is 1 meter. We are expecting the water level to come to 1 meter. Very unfortunate to see. The water level here, what happens is, it will slowly rise like this, right? So it will slowly rise like this, correct? And if we are expecting 1 meter means, it will come to 0.8 meter and stop. Clear? Water level increases and comes and stops at 0.8 meter. And beyond that, it will not increase. It stops at 0.8 meter. What was the steady state error here? So 1 meter is the final expectation. 0.8 meter is the final output here, or the final level of the water what we have seen in the tank. What would be the steady state error now? Any one of you? Stability may compromise by yes, correct, instrumentation, excellent. I will be really very happy if you name yourself instead of instrumentation. Okay, right. So excellent class. Thank you Balu, thank you very much. So now 1 meter is the requirement, 0.8 meter is the value the water level is reaching. What is the error now? After that the water level stopped, it is not changing. So the steady state has reached here. So 1 meter minus 0.8 meter, together I would be called this as a 0.2 meter, and this is called as a steady state error. Clear? So here what we do is, we try to improve the value of Kp here, and when we try to increase the value of Kp, we understood that this 0.2 meter, that steady state error will be slowly reducing, but ultimately never and ever water level reaches to 1 meter. This means always there exists a offset with the proportional controller. Clear? But many of the students, they feel that to reduce this offset or the steady state error, we have to reduce the value of okay, very good. So to reduce this value of offset, we must increase the value of Kp. But as I was saying, that is not a good job, right? Now the third one is the stability, because I have told you 3 important expectations are there. Out of that, 2 are reached. Now the third one is stability. I would like to ask you this question. If this is a closed loop system transfer function, may I know what is the closed loop pole here? So if we want to find out the closed loop pole here, how do we calculate that? So let us equate this denominator equal to 0. So if I equate this is equal to 0, in a very simple language, 1 plus Kp plus K in plus tau s, that is equal to 0. Therefore we can say tau s is equal to minus 1 plus Kp into K here. Of course we can see S can be written now as equal to like the way, all the way like this, right? Now let's take K is positive value. You take any value of K, no problem. So let us take K as 1 here. For time being, let us take this as 1, and let us take this tau is also 1, so that the calculation will become so easy. Okay, I'm very selfish here. Okay, right. So S will become now as minus of 1 plus Kp. Look at the beauty of this. If you take any value of Kp from 0 to infinity, right, any value you take, any value of Kp you take, the value of S is always negative here, correct? So that means you take Kp is equal to 10. If you put Kp is equal to 10, what will going to happen? 1 plus 10, it will become minus 11, right? So minus 11. Suppose if you keep Kp is equal to 100, then it will going to become 100 plus 1, that is 101, and minus 101. What does it mean? The pole or the closed loop system pole, let me write down closed loop system pole here. Closed loop system pole is always a negative value. Clear? So as a closed loop system pole value is always negative, I can say for the any value of Kp, you will find the closed loop pole only in the left hand side of the S plane. So if I say in a simple language, this is j omega axis, and this is sigma, and this is minus sigma, all put together we call this as a S plane here, of course, right? So you keep any value of the controller gain now, right? Use any value of the controller gain here. The value of the closed loop control pole will move in the left hand side of the S plane. So I can say for every value of Kp, the closed loop control system is stable. Have you got the final conclusion here? So first thing is about the speed of response. Yes, we have improved the speed of response by increasing the value of Kp. Have you got reduced the steady state error? Yes, of course, we have reduced the steady state error by increasing the value of Kp. Have we got the stability out of this? Yes, we got the stability out of this. Very happy, right? So if all these are true, then what is the problem to you, right? That is a simple question, isn't it? The problem with this is we were not able to make the final steady state error is equal to 0, correct? We are always having some small gap. If you are expecting 1 meter, it will come to 0.99 or 0.9 meter and leave that 0.1 meter. That's the problem with the proportional controller. Clear? Hope you really understood the whole section here, right? So are you following this or not? If you are following this, keep yes. No problem. The class may go another 5 to 10 minutes extra, but we have the patience and listen till the end. This will be very, very useful to everyone. So I need your answers. Are you clear with the data? Yes. Very good. So I am using the word like proportional band. What do you mean by proportional band? This is very important, so please be with me next 5 to 10 minutes. The range of errors for which controller output changes from minimum to maximum is called as a proportional band. Clear? For example, let us take electrical output current as an output here. Suppose if I take current as an output here, so the minimum current range is going to be 4 milliampere and the maximum current range is 20 milliampere here. Clear? Right? So we call this as a minimum output of the controller and we call this as a maximum output of the controller. Clear? Easy to understand, nothing more, nothing less here, right? Let me take two different cases here, right? Case 1. Case 1 is when the error signal is in between, like 0.5 meter here, minus 0.5 meter, and or else let me say, in case 1, the error signal or when the error is equal to minus 0.5 meter, let us say, the output of the current is generating nearly 4 milliampere, correct? At the same time, when the error is equal to plus 0.5 meter, maybe it is generating 20 milliampere current. What does it mean here? This means error when it is in the range of 0.5 meter negative value, of course, up to 0.5 meter here plus 0.5 meter, the current value will change from where to where here? Anyone? 4 milliampere here, right, to 20 milliampere here. Clear? So that means categorically said from minus 0.5 meter to 0.5 meter value of error, the controller changes its value from the lowest possible value to the highest possible value. So this range of error, that means from minus 0.5 meter to plus 0.5 meter, we call that as a proportional band. Clear? So if the error is minus 0.5 meter or if the error is minus 0.5 meter like in the tank what we have taken, so if you are getting the lowest output, look at what happens at 0.5 meter. If you are getting 20 milliampere output, then I can define this range of error from minus 0.5 meter to plus 0.5 meter is considered as a proportional band. Clear? So suppose if I say in the second case, like if the error is like just only minus 0.1 meter and plus 0.1 meter, okay? So look at this. In this case what happens? So I can say the proportional band is now very limited here, isn't it? Minus 0.1 meter to plus 0.1 meter means very, very small gap here. The output will be changed from 4 milliampere to 20 milliampere. Then you may ask a question to me, sir, what is the issue with this, right? So in general, proportional band will be given like in percentage like 100 divided by Kp. And this formula is very, very important because the more and more the value of Kp you are having, the proportional band or the range of errors the controller deals with will reduce. Clear? So that's why we should not go for the more value of the Kp. Clear? So what happens here is, suppose if we increase the value of Kp so much, naturally the proportional band will reduce. If the proportional band is reducing slowly, even for minus 0.1 meter, you will be able to see 4 milliampere. Plus 0.1 meter, you will be seeing 20 milliampere. So the operating range of error for the controller is very, very, very narrowed down. And that leads to the very, very important controller, that is on-off controller. Clear? But let me show you the practical illustration, then you will understand better way here. Suppose let us consider that this controller can generate a range of current 4 milliampere to 20 milliampere. Everyone who is going to attend Any interview, please look at this. This is a very, very important statement. Okay. So 4 milliampere to 20 milliampere is the output of the controller here. And that controller signal come to the valve here. And the valve can either shut off, that is 0% opening means it is shut off, or it can 100% open, means fully closed, fully open. 0% opening means it is closed. 100% opening means it is fully open, right? What does it mean here? It means that if the controller current is 4 milliampere, it will be fully closed. If the controller current is 20 milliampere, it is fully opened. Now I will tell you the most beautiful point. Let us say this is 1 meter height, okay? And if I call this proportional band is equal to minus 0.1 meter to plus 0.1 meter. What does it mean? This is the error range, right? So that means, let me say quickly here, the error range is this much. E of t I can say, right? What does it mean here? So anyone in the class, can you guess what do you mean by this one? Suppose if I say the error value E of t somewhere around minus 0.1 meter to plus 0.1 meter, technically what does it mean? Suppose let us take the water level is, or else let me call it here as 1 meter here. So if it is 0.9 meter, very unfortunate, look at this, 0.9 meter is the water level, 1 meter is the required level. What is the error now? Anyone? Fatafat here. Error is equal to 1 meter minus 0.1 meter. Oh my god, this leads to what? 0.9 meter. So it leads to 0.1 meter. So when the error is 0.1 meter, then immediately it will generate 20 milliampere current. When 20 milliampere current is generated, the maximum possible opening will come out of the valve, that is 100%. So suddenly the input flow rate will be so high, right? The water level will jump so much here, right? Like this, correct? Because the opening is so much, so the water level will suddenly go up. But unfortunately what happens here is, by the time when the water level reaches to 1.1 meter, then what will happen? 1.1 meter means, now what will be the error here? Error will be 1.1 meter minus, sorry, this is 1 meter minus 1.1 meter. That means required value is 1 meter and the water level right now it is 1.1 meter. This leads to minus 1.1 meter. And when the error is minus 0.1 meter, then the controller output is going to be 4 milliampere and this will generate 0% output. So when it is 0% output, suddenly the water flow will stop, and what will happen? When the water flow stops here, there is no water at all. But the outlet is completely sending the water outside, right? Then immediately the water level will come down, right? So when the water level is coming down slowly, now return, it will take return here now. Now when it is taking return here, again at 0.9 meter, what will happen? Again the controller output will become 4 milliampere, right? Sorry, 20 milliampere here, and again 100% opening will come and the flow rate will going to increase. That will actually increase the water level. Now can anybody say how the water level changes here? What are the two values of water level we can see finally because of this proportional band? Anyone? Overshoot, very good. Next, anyone? What happens here? I think backend team doesn't have any problem if I take 5 minutes extra. I am assuming that. Okay, right. So what is happening here? So the problem is the water level will toggle between 0.9 meter and 1.1 meter. Clear? By the time when the water level reaches to 0.9 meter, immediately 20 milliampere will be generated and the valve will completely open. So the water flow rate will increase and shoots up here to from 0.9 meter to more than 0.9 meter. Suddenly when water level becomes 1.1 meter, controller is so aggressive and generates 4 milliampere to turn off the valve. Because of that, the flow rate which is entering will going to cut off. Therefore, the water level again has to come down here. Clear? Excellent. Very good, Shivani. Excellent. Oscillates between 1.1 meter to 0.9 meter continuously, right? You will never get 1 meter now. Okay, it continuously goes for the cycling. And this was a question asked to me in the BARC interview. Clear? This is the reason why proportional band should not be so less, right? So if the proportional band is so less, it turns out to be on-off controller. Clear? So that's the next concept, that is on-off controller. On-off controller is very simple here. As I said, see KP, in fact, proportional band here. Very good, 1.1 and 0.9, excellent. I'm really very happy that all of you are there till the end of the video. So very good. So proportional band equal to 100 divided by Kp, as I said, right? If we keep on increase the value of Kp, right? So if we keep on increase the value of Kp, then the proportional band will reduce. And if the proportional band reduces, then you will understand that the range of error is very less. Minus 0.0012 plus 0.001 practically. What does it mean? It means that if you look at the output of the controller with respect to error signal, look at that P of t is here and E of t is here. If the error is negative value, you will be getting the lowest value of the output, then maybe that may be 4 milliampere. But if the error is positive, so this side is actually error is negative and this side error is positive here. So when the error is positive, you will be able to see 20 milliamperes output here. That is a saturated output like this. Clear? So that means only two possible outputs will be there. Either the controller will generate 4 milliampere or the controller may generate 20 milliampere depending upon the error. For a very small error, it will take aggressive action. If the error is slightly negative value, you will get 4 milliampere immediate extreme output. If the error is like slightly positive value, you will get 20 milliampere. So is it good or bad? So it is so aggressive, right? We don't really require this. If you put this on-off controller in the previous case, what happens here? So 0.9 meter to 1.1 meter we will continuously toggle, right? So that is the reason why when we keep the on-off controller to control the liquid level process, oscillation will come in the water level and we will never be reached to 1 meter because we don't want that much less proportional band like on-off controller. Clear? So it's very difficult to deal with the on-off controller as it is very aggressive. Hope you really understood these concepts, right? Putting all these things together, so if I combine everything, the very first advantage what we have seen with the proportional controller is if the value of Kp increases, then the speed of response will increase. Of course, I have told you this, right? And similarly, when the value of Kp increases, the steady state error will reduce, right? These 2 points we have taken. However, when you look at the disadvantages, as we are increasing the value of Kp very hugely, the steady state error decreases but not equal to 0. So this conclusion slide is very important. I request all of you please note down this one, okay? So it will always leave the offset. Proportional controller always leave the offset. To reduce this offset only or to make the steady state error equal to 0, we will go to the integral controller and that is your tomorrow's session, okay? But the second point is if you keep on increase the value of Kp, the proportional band will decrease and in that case, a proportional controller may turn out to be like on-off controller. Clear? The third one is for higher order plants, the higher the value of K, in fact higher value of Kp may cause the instability. See, in the previous case we have taken the liquid level tank, so Gp of S is equal to very simply like K divided by 1 plus tau S. This is a first order system. But look at that what happens here. If the plant transfer function is third order, like 1 divided by S into S plus 1 into S plus 2. For this system, if we add the value of Kp, what will going to happen? If we keep on increase the value of Kp, right, because earlier we have seen that when you increase the value of Kp, we are getting some advantages. But in this case, if we keep on increase the value of Kp, then there exists a problem of instability. The reason is the plant is third order here. Clear? So up to second order systems, the proportional controller deals very decently. But if the order of the system goes beyond second, then the proportional controller also creates the problem with the stability here. So I request every one of you, you enjoy with this problem and answer these 2 questions. This is a practice question to you. Everyone who is watching here, 40 students, you must answer this question in the comment box. Tomorrow I will look at the comment box and I will see. Once the video is out, you please keep these answers. Work out on this problem and keep the answers. I will verify with you and I will again ask this question in the tomorrow session also. So what was the first question? Find the value of Kp for which the closed loop control system is stable. This was the first question. I think most of you might be knowing this, right? And the second one is find the steady state error for the unit step input. These 2 are very good questions. And if you answer these 2 questions accurately, I can say that yes, you understood the concept very well. Okay? Hope you have got the complete picture about the total story related to the proportional controller, on-off controller. Of course, the class went little bit, very technically, because I want to cover very, very important concepts in this class. So hope I have done that decently well enough. So let me see some of the comments here. So, sir, but if the process variable goes to 0.95 while moving from 0.9 to 1.1, then E of t is 0.05. The valve opened by some. Yes, yes, absolutely correct. I really appreciate you. It's perfectly all right, right? Yes, excellent. Your statement is completely correct. Yes, but few place on-off controller also very useful. Yes, very good, Deepak. Correct. On-off controller is really useful where you want an immediate action. There oscillation को कुछ भी जरूरत नहीं है. So you need not to worry about the oscillation. Your speed of response is major important point. Correct? So that's the overall theme of the story. Hope you got clear idea about the on-off controller as well as proportional controller. If you really enjoy the video, please put it in the chat box so that I will understand how to be done for the next class. Every one of you, I am really waiting for your response. Yes, thank you, clear, very good, nice. So, well, this is the end of this session. Hope you really enjoyed with this lecture. I am thankful to the BYJU'S Exam Prep for giving this great opportunity to explain the concepts to the instrumentation students. And all instrumentation students connect to me for the tomorrow section. We will discuss the concept of integral controller. At the same time, today 9 p.m. you have a lecture on analog electronics by India's most famous teacher, Phanindar Sir. So please connect to the channel and enjoy the session. Thank you very much.